So we have seen that we can partition a group by a set of cosets. Next, we consider another way to partition a group, that is by conjugacy classes. And if we have a group G, then suppose we have two elements of G. Then we say A and B are conjugate. Conjugate of each other if and only if there exists some element x in G such that x inverse A x is equal to B. Okay, and we'll see we have seen that conjugate relation is an equivalence relation. So that means if A, so it is an equivalence relation. So it is reflexive and symmetric and transitive. Anyway, here's a definition. Let A be an element of group G. Then the subset of G defined by x inverse A and x, where x varies over all elements of G, is called the conjugacy class. Conjugacy class of G containing A. Okay, so for each element A, we can define a conjugacy class containing A. So in other words, the conjugacy class is all elements of G that are conjugate to A. Okay, and we know that conjugacy relation is an equivalence relation. That means this conjugacy class defined is an equivalence class based on conjugacy relation. So that means, as we know, any equivalence classes, uh, uh, any uh, any equivalence classes can partition a set. So these conjugacy classes can partition the group G. Okay, here's a theorem. Let A be an element of a group G, and consider, suppose the centralizer CG of A has index n. N in G. Then this element A has precisely n conjugates. Now here there are lots of terms we should review. So what is a centralizer of A? And what is an index? Okay, so for your information, the centralizer of A is all elements of G such that x inverse A x is equal to A. Okay, so it is a subset of G in which A becomes a central element. Okay, so within this subset of G, A is commutable with any elements. So that's what centralizer is. And for index, so in Lagrange theorem, we have seen index. So it is basically the number of distinct cosets uh, of a subgroup. So centralizer is a subgroup. So we can construct cosets based on this subgroup, and the index is basically the number of distinct such cosets. Okay, let's prove this theorem. So by assumption, this centralizer has index n. So that means the group G can be decomposed into n cosets, into a union of n cosets. So that is C. Let's see, CG of A x1 union CG of A x2 union and so on. CG of A xn. Okay. By the way, each of these is a coset, right coset of the centralizer. Okay, so this is okay, and we claim that the conjugates. Okay, we claim that the conjugates of A are precisely these. So using this x1, x2 up to xn, the conjugates of A are precisely x1 inverse A x1, x2 inverse A x2, and so on, xn inverse A xn. Okay, so let's prove this claim. Okay, so any conjugate of A is expressed as this, right? X inverse times A times X. So, but for if X is an element of G, then there exists, it must belong to one of these cosets, right? So that means there exists some element in the centralizer of A, and also there exists some element, some index k in from 1 to n, such that x is x is equal to c times xk, right? So any element of a centralizer, so centralizer like cg of A times xk can be expressed as c times xk, and c is some of the element, one of the elements of the centralizer. Okay, so any element in G can be expressed as this. So a conjugate of A, any conjugate of A can be expressed as cxk inverse A cxk. But inverse of product is this. But since C is an element of the centralizer, so this is equal to A. So therefore, any conjugate of A can be expressed as this, where xk is one of the elements of these, comprising the coset decomposition of group G. So this shows, this proves our claim that all the conjugates of A are precisely given by this. Okay, next we show that all these conjugates are distinct. Okay, so to do that, let's suppose we have xi inverse a xi is equal to xj inverse a xj. Okay, suppose this xi and xj come from different cosets. Okay, um, or maybe they are the same coset, but what we are going to show is that they actually come from the same coset. Okay, anyway, so multiplying both sides from the by xj from the left and xj inverse from the right, we have xj xi inverse a xi xj inverse equal to a. But this part can be rewritten as xi xj inverse inverse, and xi xj inverse is equal to a. So here we have xi xj inverse, and we have the same element here, xi xj inverse. So this means xi xj inverse belongs to the centralizer of A. Okay, and centralizer is a subgroup, remember? So from a previous lemma, this is equivalent to this. The coset with AI, xi is equal to coset with xj. So if we assume this, then xi and xj must come from the same coset. So that means if x1, x2 up to xn, if they come from different cosets, then these elements must be different. Otherwise, they must come from the, from here. We concluded that the cosets are the same. So that means all the conjugates are of this form, and they are all different. And we are done. And as a corollary to this theorem, we can say that the number of elements in conjugacy class of A divides the order of G, which is a simple application of Lagrange theorem. Okay, let's see an example. Again, we consider this dihedral group of order 8. And we want to find the conjugacy classes of this group. Okay, first of all, the center of this group, D4, is E and B. But so E and B, these are the central elements of this group. But each central group is only conjugate to itself. So nothing else can be conjugate to those central elements. So that means this E and B, these are one of the conjugacy, two of the conjugacy classes. And next, consider the conjugacy class containing A. So containing A. Okay, and we know that there is one subgroup containing A, that is E, A, B, C, which is actually found to be abelian. So this is a subgroup where every pair commute. So that means this subgroup is a subset of the centralizer of A, because centralizer is a subgroup where in which every element commute with A, and since this is an abelian group containing A, so it should be a subset of the centralizer. So this implies that the centralizer of A has the order of either 4 or 8, right? Because the order of a subgroup must divide the order of the group. But it contains a subgroup of order 4, so it must be at least 4 and at most 8. But 8 is the group D for itself. If this is the case, then that means A must be a centralizer. That means A commutes with every other element. Okay, but that is not true because the center of this group is only this, which doesn't include A. So this possibility is gone. So the order of the centralizer of A must be 4, but in that case, then this must be it. So this is not just a subset, but it is actually equal. So the centralizer of A is E, A, B, C. And next we consider all the cosets of this subgroup. But the cosets with each of these elements within the centralizer of A itself, they are closed because it's a subgroup, right? So we consider the rest of the elements, which are D, F, G, H. Okay, so let's consider this coset first. That is E, D, A, D, B, D, C, D. So that is D and AD. AD is F and BD is G and CD is H. So this is one set, and we have E, A, B, C, and D, F, G, H, and together they cover all the elements of D4. So we have D4 equals to C, G of A, and disjoint union, and C, G, A, D. Okay. In this case, we can consider this as times E. Same thing. So this means the conjugacy class containing A is given by so A times A and D inverse A D, which is A, and so D inverse is D itself. So and dA is H, and HD is C. So this is the conjugacy class containing A. And in the same way, we can find the centralizer of D as E, B, D, G. And from this, the conjugacy class containing D can be found as D and G. And also, we can find another conjugacy class containing F is F and H. So from all these, we find all the conjugacy classes, that is E and B and AC and DG and FH. So these are the conjugacy classes. So they are disjoint and collectively exhaustive. So if we take the union of all these, that will be equal to D4.